Hi everyone, welcome you all back. In this video we are going to see condensation process. Okay, the process of condensation is absolute reverse of boiling process, right? So in boiling process the water will be converted into vapor, where in condensation process the vapor is condenses into water. The vapor which has more than saturation temperature, it comes into contact with a surface at a lower temperature. For example, take your vapor is at 130 degrees Celsius and saturation temperature is 100 degrees Celsius. You know that at atmospheric pressure, saturation temperature is 100 degrees Celsius and the surface temperature is 80 degrees Celsius. Now, assume that vapor is comes contact with the surface. Because of the temperature difference, the vapor gets condenses into water at lower temperature. That lower temperature is 80 degrees Celsius. Here the condensation occurs. Here the condensation occurs in two modes. First one is film wise condensation. Film wise condensation. Second one is drop wise condensation. Right? In film wise condensation, the condensate, that is the condensed water, wets the surface here. Condensate wets the surface, forming a continuous film. Forming a continuous film which covers the entire surface. Which covers the surface. Because of this film, the heat transfer will be reduced. Because of this film, the convection process gets reduced. That is, there is no convection process. There will be only radiation process when vapor film is between the medium and the surface. So in film wise condensation, the heat transfer will get reduced. The second one is drop wise condensation. In drop wise condensation, vapor condenses into small liquid droplets. Small liquid droplets. Into small liquid droplets of various sizes. The size of the droplets will be vary, which fall down the surfaces in random manner. Which fall down in random manner. Okay, these are all the two modes of the condensation. You know that in film wise condensation, the film acts as the thermal resistance for conduction and convection process. There will be only radiation process, so the heat transfer reduces. Where in drop wise condensation, larger surface area is exposed to the vapor. So because of the larger surface area, the heat transfer in drop wise condensation is 10 times higher than the film wise condensation, right? The heat transfer Q from the drop wise condensation is greater than the heat transfer from the film wise condensation, and it is 10 times greater than the film wise condensation. So you know that the drop wise condensation is extremely wanted, right? So because of the more heat transfer, the drop wise condensation is extremely wanted, but in industrial standard, it is extremely difficult to achieve due to the commercial viability. The drop wise condensation cannot be achieved in practical conditions. So in all conditions, we are going to assume only film wise condensation only, right? So in all condensing equipment in use, we are designed on the basis of film wise condensation only. For film wise condensation, Reynolds number equal to 4 into mass flow rate m dot divided by density rho into mu, okay, which will be less than 1800, right? This is we are going to follow in the problems, right? Now let us go to the problems. Okay, take the first problem. In the first problem, it is given that dry saturated steam at a pressure of 3 bar, right? In the given data, write the first thing, pressure P given as 3 bar, okay, condenses on a surface of a vertical tube of height 1 meter. The tube surface temperature is kept at 110 degrees Celsius. So, surface temperature TW equal to 110 degree Celsius, which is equal to 383 Kelvin. And then calculate number 1, thickness of the condensate film. So, to find thickness of the condensate film is del X. This formula is available in the data book, right? So, second thing, local heat transfer coefficient at a distance of 0.25 meter. So, heat transfer coefficient is H. Here it is given as local heat transfer coefficient. So, Hx at x equal to 0.25 meter. The length of the tube or height of the tube equal to 1 meter. These are all the given data. These are all the things you are going to find out, right? So, write solution. First thing, the pressure is given as 3 bar. P equal to pressure equal to 3 bar. So, you have to take properties of steam at 3 bar. Properties of steam at 3 bar. This has to be taken from the steam table, and the saturation temperature at 3 bar equal to, you know that, 133.5 degree Celsius, and HFG value equal to 2163.2 into 10 to the power 3 joule per kilogram Kelvin. These two values you have to take from the steam table in pressure table corresponding to the pressure value as 3 bar, right? Next step, we know that as usual film temperature has to be find out. TF equal to, here T surface temperature, here TF equal to T surface temperature plus T saturation temperature divided by 2. It is 110 plus 113.5 divided by 2, which will be equal to 121.75 degree Celsius. Now you have to take the properties of saturated water at this temperature. So, now at approximately 120 degrees Celsius, properties of saturated water from HMT data book, page number 21. You have to write density equal to 945 kilogram per meter cube and kinematic viscosity nu equal to 0.247 into 10 to the power minus 6 meter squared per seconds. The thermal conductivity value K equal to 0.685 watt per meter Kelvin, and mu, you know that it is rho into nu. This you have to calculate. This will be 2.33 into 10 to the power minus 4 Newton second per meter squared. Okay. Now, next thing in the problem, you are asked to find out the thickness, film thickness value and local heat transfer coefficient. For that, you have to refer the data book. Go to the data book. So, this is the data book. In the page number 148, in this version of the data book, in page number 148, the formulas are given for condensation. In condensation, for film wise condensation, for vertical surfaces, for horizontal tubes, bank of tubes, vertical tubes. For all these things, the formulas are available here. In our problem, it is given that it is film wise condensation and vertical surfaces. For vertical surface, the value of boundary layer thickness, that is film thickness, del X value you have to find out in the first division. So, this formula you have to write down, del X equal to 4 mu L Kx Tv minus Ts. Here Tv is nothing but vapor temperature, which is 133, right? So, surface temperature is 110 degrees Celsius, right? This formula you have to take for del X, and for Hx value K divided by del X. This formula I have to take. So, okay, these two formula I will write now. So, first thing, for vertical surfaces from HMT data book, page number 148. The formula for del x is given as 4 mu k x into T saturation, that is T vapor minus TW divided by here TV, that is vapor temperature equal to saturation temperature, right? TW equal to surface temperature. These two values you have to take, divided by G into HFG rho squared to the power 0.25. All these values you have to substitute now. 4 into mu is 2.33 into 10 to the power minus 4 into k value is 0.685 into x value is 0.25 into 133.5 minus 110 divided by G value is 9.81 into HFG is 2163.2 into 10 to the power 3 into rho value is 945 to the squared and the whole bracket 0.25. Okay, if you solve these values and you will get the answer as del x equal to 1.18 into 10 to the power minus 4 meters, which can be written as 0.118 millimeter. Okay, you already know that the film thickness will be always in terms of millimeter. If it comes in the meters, then your problem is wrong, right? So now go to the second subdivision. In second subdivision, you are asked to find out the Hx value. Here Hx formula is k divided by del x. Here k value is 0.685 divided by del x is nothing but del x has to be substituted in meters, 1.18 into 10 to the power minus 4, okay, which is equal to 5775.2 watt per meter squared Kelvin. This is the value of Hx. Okay, now go to the second problem. Okay, this is the second problem. In second problem, it is given that a vertical tube of 65 mm outside diameter. So write the given data. Given outside diameter D equal to 0.065 meters and it is 1.5 meter long. So L equal to 1.5 meter and it is exposed to steam at atmospheric pressure. The outer surface of the tube is maintained at a temperature of 60 degrees Celsius. So write the given data. TW equal to 60 degree Celsius, which is equal to 333 Kelvin. 273 plus 60 equal to 333 Kelvin and maintained at a temperature of 60 degrees Celsius by circulating the cold water through the tube. Calculate number 1 rate of heat transfer to the coolant, second one rate of condensation of steam. So to find rate of heat transfer is called as Q. Rate of condensation is called as m dot. In boiling, we also know that rate of boiling is known as m dot. Here, rate of condensation is known as m dot. Okay. So the first thing you have to take. So the pressure here given is atmospheric pressure. We know that at atmospheric pressure, T saturation equal to 100 degree Celsius and at 100 degrees Celsius HFG equal to 2256.9 into 10 to the power 3 joule per kilogram Kelvin. Okay. So now the second step is to find out the film temperature. Film temperature TF equal to TS plus TW divided by 2. Okay, which is equal to 60 plus 100 divided by 2, which is equal to 160 divided by 2, which is 80 degree Celsius. So the film temperature is 80 degree Celsius. The next step is you have to take the properties of saturated water. Properties of saturated water at 80 degree Celsius from page number 21 of HMT data book, right? The values are, density value is 974 kilogram per meter cube and the new value is 0.364 into 10 to the power minus 6 meter square per seconds. K is equal to 0.6687 watt per meter Kelvin. Now from these values you have to find out the dynamic viscosity value nu into rho. That value will be 354.53 into 10 to the power minus 6 Newton second per meter squared. Now you have to assume laminar flow. Assume laminar flow. First thing you have to find out the Q value, heat transfer value. You know that Q equal to HA del T. Here del T is nothing but your T saturation minus TW. So here area is given, that is the diameter, outside diameter, and the length of the tube is given. So you have to find out the H value only. So now for H value from HMT data book you have to take the formula. So H equal to 0.943 into K to the power 3 density to the power 2 G into HFG divided by mu into length of the tube TS minus TW to the power 0.25. This formula is available in data book in condensation page. Here for vertical surfaces, for H value this formula is given here. Okay, 0.92943, that formula I have written here, right? So substitute all the values in this formula, you will get the value of H as 3908.86 watt per meter squared Kelvin. Okay, now the heat transfer value has to be calculated, which is HA del T, which is equal to 3908.86 into area is nothing but your surface area, outer surface area. The outer surface area is known as pi dl. So here the value of d is given as 0.065 into length of the tube is 1.5 meters into TW minus T saturation, that is del T value is 100 minus 60 degree Celsius. So the answer will be 47892.18 watts. So this is your Q value, right? So the next thing you have to find out the rate of condensation. Rate of condensation, m dot have to be find out. So m dot, so you know the formula Q equal to m dot into HFG. So now you know the value of Q and HFG value is already taken from the data book, which is equal to 2256.2 into 10 to the power 3. So substitute these values, you will get the m dot value as 0.0212 kilogram per seconds. Okay, in the problem already we have assumed that this is laminar flow, right? So to find whether the assumption is correct or not, you have to find out the Reynolds number value. Already you know the formula, 4 into m dot divided by rho into mu. So 4 into 0.0212 divided by the rho value is 945 into 354.33 into 10 to the power minus 6. Substitute all the values, you will get the answer 1171, which is less than 1800. So the flow is laminar. So assumption is correct. Okay. So this is the answer for this question. Okay, thank you all. In the next video we will solve some more problems on condensation process.